Hey everyone, it's Suraj, and today we're going to be walking through discussion 9 from Spring 2019's iteration of Data 100. So what I want to emphasize is that this is not a replacement for lectures, so I highly recommend you are all caught up on the classification and logistic regression lectures before watching this. But with that being said, before we get too deep into the discussion, we'll go over a quick overview on the difference between regression and classification. Okay, so in both cases, our input we can say to be xi, which is a vector of real numbers, okay, which we can say is our data point. Okay, and the difference between regression, which is what we've seen so far, and classification, which is what we're seeing now, is with regression, given a data point, we wanted to predict some real number. Okay, so for example, given a student's midterm 1 and midterm 2 scores, you want to predict what their final exam grade will be, or something like that. Okay, so predict a real number. The difference with classification is also, given the same vector of real numbers, you want to predict a class label, so a discrete label. So for example, you want to predict whether or not, so yes or no, if a patient has a certain disease, for example. And this is not a new idea, right? Because in data 8, you will have done things like k nearest neighbors, which is also a classification technique, right? Given a data point, you look at all the points closest to it, and from there, you'll determine what label to assign your point, right? So you want to predict a label. So that's the main difference between regression and classification. The inputs are the same, so a data point, but the output for regression will be some real number, whereas for classification, we want to predict some label. Furthermore, in this class, we'll be dealing with binary classification, at least just when we're talking about logistic regression, which is predicting whether or not a point belongs to class 1 or class 0. You can think of these as being yes or no, but all we'll really care about are these two classes, 1 or 0. And so now the question is, where does logistic regression come in? So logistic regression on its own is not a classification technique. Logistic regression is another form of regression where the outputs are restricted to be in the range 0 to 1. Okay, so we can write that. Logistic regression outputs are continuous in the range 0 to 1. Well, that's convenient because we know probabilities also are real numbers that are continuous in the range 0 to 1. So how we use logistic regression for classification is that we pair it with some decision boundary or a threshold. So our classifier, when we deal with logistic regression, is usually something like 1 if the probability that y is equal to 1, and we say y is our class label, given x is greater than or equal to 0.5, and 0.5 is just the example decision boundary / threshold that I chose, but it could really be anything. And we'll say class 0 if it's below the threshold. So if the probability that y is 1 given x is less than 0.5. But again, 0.5 could have been 0.7, for example. It's not set in stone that we have to use 0.5. So logistic regression on its own, again, the output of the sigmoid function, which is what we'll see later in this discussion, is some continuous number in the range 0 to 1. How we change this to, how we modify that to be a classification is we pair it with a threshold. We say if the output is above 0.5 or 0.7 or whatever, it belongs to class 1, but if it's below, it belongs to class 0. So for example, if the probability of a patient having a certain disease is greater than 0.8, you'll say they have the disease. If it's below 0.8, you'll say they don't have the disease. Okay, so that's how we change that's how we interpret the outputs of logistic regression as being discrete labels, either 1 or 0. Okay, with all of that in mind, we can dive into some of the problems on the worksheet. So in the first one, we just have some true or false questions. So 1, a binary or multi-class classification technique should be used whenever there are categorical features. And so the answer to that is false. Okay, and this one is meant to trick you because you're thinking about categories and discrete labels, but really the inputs to a classification problem can be anything. There's no restriction on them, right? You can use categorical features, right, which you can do with standard linear regression as well. You can do that using one-hot encoding, but the outputs of classification techniques are categorical, right? They're discrete labels. The features themselves, the inputs to your model, can be anything. So there's no restriction on features. Cool. B, a classifier that always predicts 0 has a test accuracy of 50% on all binary prediction tasks. That's also false. Right? Just because you always predict class 0 doesn't mean you will be right 50% of the time. So for example, if you wanted to predict, if your classification problem is predicting whether or not students pass an exam, and let's say like 90% of students end up passing, so 90% of students belong to class 1, if you predict 0 all the time, you're not going to have 50% test accuracy, right? You'll have something closer to 10% test accuracy. And so the bigger reason why this is false is because we have no knowledge of the distribution of the test set when we're creating our model, right? So we have no knowledge of distribution in test set. When we're creating our model, we don't know what the test set will look like, so it's impossible to tell what our test accuracy will be. Okay, and just by predicting 0, it doesn't mean that 50% of what we test will be zeros and 50% of it will be ones. Okay, so we can't say that. C, for a logistic regression model, all features are continuous with values from 0 to 1. Again, that's false. The outputs of logistic regression are continuous with values from 0 to 1, but the features themselves have no restriction, right? The inputs to your logistic regression model could be anything, right? Any vector of real numbers. Okay, so that's false, and it's sort of meant to trick you, right? All of these questions are sort of tricky. Okay, but really, it's for a similar reason to part A. And D, in a setting with extreme class imbalance in which 95% of the training data have the same label, it's always possible to get at least 95% testing accuracy. Again, this is false for a similar reason to part B. We don't know what the distribution of points in our test set will be. Maybe there's an extreme class imbalance in the opposite direction in our test data, right? We really don't know what the distribution of our points in our test set will be, so it's hard to make claims like this. Okay, so it turns out all 4 of these were false, and they're all very tricky. So I highly recommend you make sure you get why each of these are false. Okay, number 2, based on the scatter plot of the data below, draw a reasonable approximation of the logistic regression probability estimates for the probability y is 1 given x. Okay, so what we know is towards the endpoint, so over here and over here, all of the points either belong to class 1 or class 0, and there isn't that much uncertainty, right? So over here, we're almost certain that our point belongs to class 0, so the probability that it belongs to class 1 is pretty close to 0. Similarly, over here, we'd be pretty sure that our point belongs to class 1, so the probability that it belongs to class 1 is pretty close to 1. Now, it's in this middle region where most of the uncertainty lies. So that's where the probability of belonging to class 1 will be closer to 0.5. Like, we're not that sure either way. And so, as a result, the curve will probably end up looking something like this. Whereas in this middle region is where all of the uncertainty lies. That's where there's a lot of overlap between points that are class 1 and class 0. Okay, and I guess this is a good opportunity to illustrate what I mean by having a threshold, right? And so if this is our estimate for the probability y is 1 given x, and let's say this is our threshold, if a probability is above this threshold, we'll classify our point as being in class 1, and if it's below this threshold, we'll classify it as belonging to class 0. Okay, but that wasn't particularly relevant to this problem. That's just something that I thought I should mention. And so now in question 3, we're told that our friend argues that this set of data is linearly separable because I can draw this line over here and say everything above the line belongs in one class and everything below the line belongs in another. So we have to determine whether or not this friend is telling the truth, really. Is this data linearly separable? So before we answer that question, I think it's important to determine what exactly it means for data to be linearly separable. And so we'll take a look at these slides that I had from last semester. And this formal definition is important. Okay, a set of d-dimensional points. So in this case, our points are really one-dimensional, right? The y value is just the class label, but the x's on their own are just single scalars, so they're one-dimensional. Is linearly separable if and only if we can draw a degree d minus 1 hyperplane to separate the points. And so again, for us, the degree d is 1, so we need to be able to draw a hyperplane of degree 0, which is really a line of the form x is equal to a. Okay? We need to be able to draw such a line, so a line of the form x is equal to a, which is just a vertical line, and use that line to separate our points. And clearly, in this example, there's no such line I could draw. Right? There's nowhere I could draw a vertical line here and say everything to the left is in one class and everything to the right is in another. And part of the problem with this question is that the plot is misleading, okay, because we're showing the class label in two different ways, both with the height, right, with 0 and 1, but also with the color, right, with the reds and the blues. A more representative plot would be something like this, where everything is laid out on a number line, and you can clearly see what the classes the points are, and you can also clearly see the fact that there's no point at which you can draw a vertical line and say everything to the right is in one class and everything to the left is in another. Okay, there's nowhere I can draw such a line like this, so no such line, and so therefore here this is not linearly separable. Okay, so in order to make this a little more clear, highly recommend you make sure you know what the definition of linear separability really is. Now we'll move on to the last problem, question 4. We're told we have a classification data set consisting of two xy pairs, 1, 0, and -1, 1. So really here our points are 1 and -1 with class labels 0 and 1, because y represents the class. Okay, and we're told that the covariate or the feature vector for each is a two-element column vector that looks like 1 in the scalar x. So the vector, big X, is 1 in the scalar x, and that allows us to get a bias term, right? And so we say the probability that the class label is 1 given this vector x is the sigmoid of x transpose beta, where beta is a column vector that looks something like beta naught and beta 1. So when we look at x transpose beta, it really looks like beta naught plus beta 1x, which is really a line of the form y is equal to mx plus b. So that's what we're passing into the sigmoid function, which, as we've seen in lecture, is 1 over 1 plus e to the negative t. So in this problem, we're not going to deal with how we come up with these estimates for beta. We're just going to calculate the probability that y is 1, given that x is this vector 1, 0. And so first we need to compute x transpose beta, right? Because then we plug that in to the sigmoid function. In this case, x transpose is 1 and 0, and beta is -0.5 and -0.5. So we do this dot product. We get 1 times -0.5 plus 0, which is -0.5. So that means the probability y is 1 given x, with this specific x, is sigmoid of -0.5, which is 1 over 1 plus e to the 1/2. Okay, because in the sigmoid we take the negation of the argument, but our argument's already negative, so it ends up being 1 over 1 plus e to the 1/2. Okay, so now in part B, we're taking a look at cross-entropy loss, and we sort of need to compute the loss over the data set that we're given. So I don't want to go too deep into where cross-entropy loss comes from. Again, this is not a substitute for lecture, but one way you can think of cross-entropy loss is being the difference between two probability distributions. Okay, so if the cross-entropy between two distributions is large, it means they're very different. And if it's small, it means they're close to one another, okay, in terms of the outputs that they have. So if we minimize the cross entropy, we're minimizing how different our predicted distribution is compared to the actual distribution. So minimizing cross entropy minimizes this difference. Okay, and so for B, we're told that beta, just suppose it's beta naught and beta 1, explicitly write out the empirical risk for this data set 1, 0 and negative 1, 1 as a function of beta naught and beta 1. Okay, so essentially what we need to do is compute this expression for both the point 1, 0 and the point negative 1, 1. And then we can put those two things together, sum them up, and multiply it by negative 1/2. Okay, and so notice there's this component xi transpose beta that ends up being very important in both of these, in all of these cases, right? So what we'll do is we'll end up computing first this term and then this term and put that all together. So for both of these, we really need to calculate xi transpose beta first. In this first point, remember the vector x is 1 and the scalar x. So here we have 1, 0, and beta being beta naught, beta 1, which tells us xi, this should be a 1. So xi transpose beta is just beta naught plus beta 1. So first we need yi xi transpose beta, which in this case is 0 because yi is 0. Then we need negative xi transpose beta, which is just negative the sum of beta naught and beta 1. Okay, so we know the first part of our expression for the risk will be negative 1/2 times 0 plus log of sigmoid of negative beta naught plus beta 1. Okay, so that's this entire expression for our first point. So we need to do the exact same thing for our second point as well. And so first we can calculate xi transpose beta as being 1, negative 1, beta naught, beta 1, which gives us the difference of beta naught and beta 1. Yi xi transpose beta, since yi in this case is just 1, this is just the same thing. And then negative xi transpose beta is just the reverse of this. So beta 1 minus beta naught. Okay, so we've computed these pieces for both scenarios. Not both scenarios, both data points. So now I can plug this in again. So now plus, I need yi xi transpose beta for the second point, which is beta naught minus beta 1, plus log of sigmoid of negative xi transpose beta, which in this case will be beta 1 minus beta naught. Okay, lots of close brackets there, but over here, just to make it a little more clear, that's beta 1 minus beta naught. Okay, so we've put a lot of these pieces together. Now it's just a matter of how are we going to simplify all of this. And so the simplification we'll actually do now in part C, when we plug in beta is equal to negative 1/2 and negative 1/2. So what we'll do is just plug in beta naught is a negative 1/2 and beta 1 is negative 1/2. Okay, to do some simplifications though, we notice we have a log of a sigmoid of something, right? And so we can actually rewrite that. So log of sigmoid of t, let's just say, is the log of 1 over 1 plus e to the negative t. But using log rules, I can write that as log of 1 minus log of 1 plus e to the negative t. But log with any base of 1 is just 0. So I can write this as negative log of 1 plus e to the negative t. So that'll help us in some of our simplifications. So again, I'm passing in beta naught and beta 1 are both equal to negative 1/2. So now my risk in terms of beta is still negative 1/2 times negative log of 1 plus e to the negative t. But in this case, t is already negative. Okay, t is negative beta naught plus beta 1, which is just negative 1. Right? There's a lot of negatives going on. But t which is the thing that we're passing into the sigmoid, is negative beta naught plus beta 1. And beta naught plus beta 1 is negative 1, and the negative of that is just 1. So that means we end up having an e to the negative 1 in here, because we're taking the negation of t. Okay, so that's that. Plus, now here we have a beta naught minus beta 1, but the difference between two equal terms is always going to be 0, right? So that's a plus 0. And then now we have a log of a sigmoid of beta 1 minus beta naught. So that will again be minus log of 1 plus e to the negative whatever's in here. So the negative of beta 1 minus beta naught is just beta naught minus beta 1. But that difference is equal to 0, right? Because they happen to be equal. And so we have log of 1 plus e to the 0. And now we have some things that we can simplify. First, we notice there's a negative 1/2 out here. So we can distribute it and make all of our terms positive. So we can have 1/2 of log 1 plus 1 over e plus log of 2. But then using the log rule, that log of a plus log of b is the log of the product. I can combine these two things. And I have 1/2, log 2 plus 2 over e. Okay, and I believe that's what this works out to be. So that's the empirical risk for this data set, where our observations are 1 with class 0 and negative 1 with class 1, with the beta, fitted beta being negative 1/2 and negative 1/2. It's a lot of arithmetic, and we went through it pretty quickly, but I highly recommend you either watch this again or take a look at the solutions to make sure you can work out all of these calculations on your own. Okay, D, are the data linearly separable? So I think to make it easy, let's take a look at the plot. So remember, our 2 points are 1 with class 0 and negative 1 with class 1. So 1 with class 0, I can say this is class 0. We have that. And then negative 1 with class 1 is over here. Now the question is, can I draw a hyperplane to separate the two classes? And yeah, I can. This hyperplane over here separates the two classes. Oops. But that's actually not even the only one that separates the two classes, right? I could draw this one, or this one, or this one. The standard one we would choose is the one that's exactly in the middle. So the line x is equal to 0. But actually, any of these actually work. But in terms of choosing which one of these hyperplanes is the best, we would choose the line x is equal to 0. And for the reasoning behind that, either wait till you take future courses, or they may have talked about it in lecture. But that's sort of out of the scope of this discussion. So the last problem, does your fitted model minimize cross-entropy loss? I don't think that's worded too well. I think the main takeaway from this problem is, if your model is linearly separable, then your training error will be 0, right? Because you can just set your decision boundary to be that hyperplane, right? So in this case, I could set the decision boundary to be this line, x is equal to 0, and say my classifier is everything to the right is in one class, everything to the left is in another. And if it's linearly separable, your training error will be 0. So I think that's the main takeaway from this problem. And I think that actually wraps up the entire discussion. So again, feel free to comment on Piazza if you have any clarifying questions with this discussion. If you're studying for the midterm on Thursday, good luck. And yeah.